Oftentimes, when we're finding the probability of an event A, especially when the event we're trying to describe is best addressed with the classical probability view, we have to count the number of ways that event A can occur and divide that by the total number of ways that any event in the sample space can occur. Sometimes counting these events can be a little tricky, so much so that there's an area of mathematics called combinatorics that deals with counting. In this video, we'll talk about a few counting techniques that will help us quantify probabilities of particular discrete random variables. One of the more basic approaches to counting is with the multiplication rule for counting. Simply put, if an operation can be performed in n1 ways, and if for each of these a second operation can be performed in n2 ways, then the two operations can be performed together in n1 times n2 ways. For example, say we work for Norman, Oklahoma's fourth largest cracker factory, and our product line has two different styles of crackers that come in 3 varieties and in 5 different count sizes. So how many different packages do we need to design? 2 times 3 times 5, or 30 different package designs. For another example, much is made lately of alternate college football uniforms and how many combinations of uniforms that can be produced. Let's say a team has 4 possible helmets, 8 possible jerseys, 6 possible pants, 3 colors of shoes, and 2 colors of gloves. How many uniform combinations are possible? 4 times 8 times 6 times 3 times 2, or 1,152 combinations. Let's look at one more example of the multiplication rule for counting. Say that a state license plate has 6 characters, and say that the plates are of the form 3 letters followed by 3 numbers. How many ways are there to construct a license plate? We have 26 options for the number of letters, and we have 10 digits, or 0 through 9, for the possibilities of a number. For letter, we have 26 times 26 times 26 possibilities. For number, we have 10 times 10 times 10. Therefore, the total combinations to appear on a license plate is 17,576,000. Alternatively, let's say that the 6-character license plate can be made up of any letter or any number for all 6 characters. For any one character, there are 26 letters and 10 numbers, or 36 possible characters. Therefore, the number of possible license plates is 36 to the 6, or just over 2.1 billion possibilities. A function that is useful in counting is the factorial function. The notation for a factorial is an exclamation point. So n exclamation point is not n, but it's read as n factorial. The factorial function is pretty simple. N factorial is equal to n times n minus 1 times n minus 2 all the way down to 1. For example, 3 factorial is 3 times 2 times 1. By definition, 0 factorial is equal to 1. One example of where a factorial on its own is useful in counting is when we are ordering n objects. Say we have 5 books and we want to put them on the shelf. How many ways are there to order the 5 books on the shelf? How many options do we have for the first book to place on the shelf? 5 books, so 5 options. Once we have placed that book on the shelves, how many options do we have for the second book? Since 1 is already placed on the shelf, we only have 4 options remaining for the second book, and only 3 options for the third book, 2 options for the fourth, and only 1 option for the fifth to be placed on the shelf. As a consequence of the multiplication rule for counting, we have 5 times 4 times 3 times 2 times 1, or 120 ways to arrange the books. That's 5 factorial. Let's think about a completely different example. Say we have 5 students, A, B, C, D, and E, who are equally worthy of a scholarship, but we only have 2 scholarships that are exactly the same to hand out. How many ways are there to choose the 2 scholarship recipients? Let's enumerate the possibilities of scholarship recipients. The 2 recipients could be A and B, or A and C, or A and D, and so on, for a total of 10 possibilities. We can enumerate these possibilities, but that will take more and more time to do the larger the problem gets. The next counting function is called a combination, and it's used to count the number of ways that R elements can be chosen from N elements without regard to order. That is, it's the number of combinations of N distinct objects taken R at a time. On the screen, you'll see a couple of common ways we write a combination, said as N choose R. The function is written as n factorial divided by r factorial times n minus r factorial. To calculate our scholarship recipients, 5 choose 2 is 5 factorial divided by 2 factorial times 3 factorial. 120 divided by 2 times 6, or 10. Similar in concept to combinations, but where the order of selection is important, is another counting function called a permutation. The notation for the selection of r elements from n elements, where the order or arrangement of those r elements is important, is shown on the screen. Let's go back to our scholarship example, but let's assume that the two different scholarships are different. One is the Switzer scholarship, and the other is the Stoops scholarship. How many ways are there to allocate these two different scholarships to a possible 5 students? Let's enumerate these possibilities. A gets the Switzer scholarship and B gets the Stoops scholarship, or B gets the Switzer and A gets the Stoops scholarship, such that AB is different from BA because arrangement matters. Or there's AC and CA, AD and DA, and so on, for a total of 20 possibilities. How many ways are there to give out the Switzer scholarship? We have 5 students, so 5 ways. Then how many ways are there to give out the Stoops scholarship? If we've already given out 1, there are 4 remaining students, so 4 ways. 5 times 4 is 20. In a way, this is a factorial that's truncated. How do we truncate the factorial? We take n factorial in the numerator and divide by n minus r factorial. This is a permutation. For the scholarship example, we have 5 factorial divided by 5 minus 2 factorial. Another way to think about this problem is to first select 2 recipients out of the 5 students and then order them. How many ways are there to generally choose 2 out of 5? With a combination, 5 choose 2. Once we have our 2 recipients, how many ways are there to assign the scholarships? We have 2 options for the first scholarship and then 1 remaining option for the second, or 2 factorial. That is, we can calculate the combination and then multiply it by r factorial. This gives us the relationship between the permutation and the combination and shows how order matters in the permutation. Note that permutations tend to give us many more possibilities, r factorial times more possibilities. Let's say you're a reliability engineer at Bright Idea Incorporated, which is obviously a light bulb manufacturer. You're going to perform a life testing experiment on some light bulbs, and you have a batch of 4 40-watt bulbs, 5 60-watt bulbs, and 6 75-watt bulbs. Let's say you pull 3 of those light bulbs at random. How many ways are there for you to pull a sample that has exactly 2 75-watt light bulbs? First, we have to find the number of ways to pull 2 75-watt bulbs from 6, or 6 choose 2, which is equal to 15. Then we have to find how many ways to pull the remaining 1 light bulb from the rest of the 40-watt and 60-watt bulbs, or the rest of the 4 plus 5 equals 9 bulbs. That would be 9 choose 1, which is equal to 9. From the multiplication rule for counting, we know the number of ways to get 2 75-watt bulbs, and we know the number of ways to get the remaining 1 bulb. We multiply these 2 values together to get 135 different ways to get our desired sample of 3 bulbs that contain exactly 2 75-watt bulbs. If we define event A as pulling 2 75-watt bulbs out of 3 bulbs, the probability of A would be described with classical probability. We know how many ways there are for event A to happen, and we know exactly how many ways there are to pull 3 light bulbs out of 15. In the numerator, we'd have 135. In the denominator, we'd have 15 choose 3, or 455 ways. The probability of A would then be 135 divided by 455, or 0.297. As you can see, counting is important for calculating probabilities of events that are described with classical probability. And in upcoming videos, we'll see how counting is also important in the probability distribution functions of a few discrete random variables.